Welcome to the Explainer. Today we are diving deep into the architecture that is, and this is no exaggeration, changing our world. It's the engine behind everything from ChatGPT to incredible scientific breakthroughs. We're talking about the Transformer. And to kick things off, let's start with a quote from, get this, over 250 years ago. It's wild to think that Samuel Johnson, way back in 1759, perfectly captured the single most important idea behind this technology. It really sets the stage for everything we're about to unpack. You've definitely seen the headlines. You've almost certainly used the tools it powers, whether you realized it or not. But what is the Transformer, really? Well, it's a type of neural network that has completely rewritten the rules of AI. It's not just about text anymore. This thing is tackling huge problems in science, generating art, and even mastering complex games. All right, so here's our game plan. We're going to peel this thing back layer by layer. We'll start with the big picture and then zoom all the way down to the clever little mechanisms that make it all tick. Let's get into it. So let's get right to it. What is a transformer at its heart? It's a model that is exceptionally good at predicting the next word in a sentence. And it does that by understanding the relationships between all the words in a sequence, even if they're super far apart. This ability to see the whole picture at once, that was the massive leap forward. It was a total game changer compared to older models. And to really get why, we need to talk about the revolution it started, which all comes down to one word: attention. And that brings us to the core idea, the real breakthrough, this concept called attention. Now, to truly appreciate how revolutionary this is, you gotta understand what the world looked like before it came along. I love this analogy. Think about the old way. With models called RNNs, it was like a long assembly line or a game of telephone. Information got passed down step by step, and by the time you got to the end of a long sentence, the context from the beginning could be, well, kind of fuzzy or lost altogether. Transformers are completely different. They're like a round table discussion where every single word can talk to every other word at the exact same time. Nothing gets lost in translation. And this round table idea isn't just a neat metaphor. It has a massive, massive practical benefit. You can process everything in parallel. Because all the information is handled at once, you can train these models on just colossal amounts of data and do it way, way faster. This is the key that unlocks the current AI boom. Okay, so how does this roundtable actually get its work done? Well, it all happens inside the basic, fundamental unit of the model, which is called the transformer block. You see, a full-blown transformer isn't one single, impossibly complex thing. It's actually much simpler. It's just a whole stack of these identical blocks, one on top of the other. Each block takes in information, chews on it, adds more context, and then passes its refined understanding up to the next block in the stack. It's like a continuous process of enriching the meaning of every word. Inside each of these blocks, there are basically two main jobs getting done. First, you have the attention mechanism, that's our roundtable, where all the words talk to each other to figure out the context. Then, after that conversation, a feed-forward network takes each word's new, context-rich meaning and just thinks about it, processing it individually to add even more depth. And then you have these two other crucial players, kind of like the support crew that keeps the whole show on the road. Residual connections are like little shortcuts or express lanes, letting the original information skip some steps so it doesn't get watered down in these super deep networks. And layer normalization is just a clever trick to keep all the math stable and prevent the numbers from exploding during training. Now, let's zoom in on the real star. All right, this brings us to the absolute heart of the machine, the real secret sauce, self-attention. This is the mechanism that lets the model decide for every single word which other words in that sentence are the most important for understanding its meaning in this specific context. So how does it do this? Well, it uses this really clever system. For every single word, or token as it's called, the model creates three special instructions, or vectors, to manage the conversation. They're called the query, the key, and the value. This is where the magic really happens. First up is the query. You can think of this as the word itself asking a question, like, hey, who in this sentence is relevant to me? Who can help me figure out what I mean right here, right now? It's sending out a search request for context. Now, that query goes around and looks at every other word's key. The key is basically like its library card catalog entry. It's a label that advertises what kind of information that word has. The model compares the query to all of the keys to find the best match. And once it finds the right key, it grabs that word's value. The value is the actual stuff, the content inside the book, the real substance of that word's meaning. So, query asks the question, it finds the right key, and it pulls the value to enrich itself.
So what's happening under the hood is a bunch of math, but the idea is simple. The model calculates a relevance score by comparing a word's query with every other word's key. A high score means a strong connection. These scores then become weights that determine how much of each word's value gets mixed into the current word's new representation.
But here's where it gets even cooler. The model doesn't just ask one question. It uses something called multi-head attention. This is like having, say, 8 different librarians at that round table, all asking different kinds of questions at the same time. One might be looking at grammar, another at semantic meaning, a third at cause and effect, all at once. And the beauty of it is, the outputs from all these different heads, all these different perspectives, get bundled together. They're combined to create one single, incredibly rich, multifaceted representation of that word that captures all those different nuances.
Okay, hold on a second. If everything is happening at the same time at our round table, how on earth does the model know the order of the words? Right? Without order, the dog chased the cat and the cat chased the dog would look exactly the same to the model.
Right, this is a great question, and the solution is actually pretty elegant. It's called positional encoding. Before any of the words even go into the first transformer block, the model just adds a little bit of information to each one, a unique vector that says, hey, your word number 1, your word number 2, and so on. It's like giving each word a permanent address in the sentence. Okay, so we've got the whole architecture built, but right now it's just an empty machine full of random numbers. How do we turn it into something as powerful as ChatGPT? Well, that happens through a really fascinating multi-stage training process. The best way to think about it is like sending the model to school. First is pre-training. This is like general education, where it reads basically the entire internet to build up a massive foundation of knowledge about grammar, facts, and how the world works. Then comes supervised fine-tuning. This is like studying with a tutor who gives it perfect examples of questions and answers, so it learns the style of being helpful. And finally, reinforcement learning. This is like doing practice problems, where it generates its own answers, humans rank them from best to worst, and it learns from that feedback to get better and better. And this leads to a really crucial point. When you're chatting with an AI assistant, you're not talking to some kind of conscious being. You are, in essence, interacting with a statistical echo of the thousands of human labelers who created its training data. It's a highly sophisticated mimic that has learned to reproduce the patterns of what those humans considered a good answer. So, we've gone on quite a journey, right? From the big picture impact all the way down into the nitty-gritty math and back out again to how these things are trained. So what does this all mean for what's coming next? Well, because this architecture is so incredibly flexible, the future is looking pretty wild. We're already seeing multimodal models that can understand text, images, and audio all at once, seamlessly. And as these models get bigger and bigger, we're seeing these bizarre emergent abilities pop up. Skills they were never actually trained to do, but that just appear. And that leaves us with this really mind-bending thought to wrap up with. That last step of training, reinforcement learning, it allows models to discover what works best on their own. That opens the door to them finding solutions and strategies that are completely outside the box of human intuition. So, what happens to science, to creativity, to problem solving, when our tools can think in ways we literally can't? We'll dig into that very question in our next explainer.